words, and we're going to try to see what you're drawing. So, okay? I know it seems a little odd right now. I'll get to it. Okay, we'll do it probably right on the first one.
Is this just review?
What?
Is this just review?
Nope, this is brand new. Brand new stuff. So, all right, here we go. It's not clicking. It doesn't want me to click. Ah, there we go. Okay, today's goals. Let's go through this first. Number one, we got a bunch of postulates we got to talk about today. We got 2:8 to 2:11. Now, we've already went through the first 7. We had one theorem so far. We're going to look at theorems maybe on Monday. We have a couple more theorems on Monday. But today was to talk about our 4 postulates. We have 4. I think they're incredibly easy. But again, I've seen them a lot, so I already know the basics on them. But I want to discuss them today. That's kind of the idea. And give you some examples of them. Okay? We're going to do a bunch of examples of the first type, maybe 1 or 2 of the second type. So I have more examples of the first few postulates than the last 2. Just because we're going to save a lot for Monday. Homework we have due for Monday. So if you were gone yesterday or you weren't paying attention, we had homework due. It's on the board over there. You can see it's page 139. Okay? Page 139, 1 through 7, 9 through 15, 17, 18, 23 through 26. Those are my homework problems. Make sure that you're working on them. Make sure that you know what you're doing. If you have not finished that worksheet 2.6, you need to differentiate your homework and you got to do the extra stuff, or you have to do the extra steps because you haven't earned the right to do shortcuts yet. Okay? So keep that in mind. You got to make sure you earn the right to do shortcuts in here. So you got to get that worksheet 2.6 turned in because now it's late, multiple days late. So get that done, get it turned in. Okay, questions at all about what we're doing here? Now, before we get to the first one, here's what I'd like you to do. I'm going to turn on the lights here in a second, I'll get to them, okay? I want you to think about a drawing, so you're going to need a piece of paper and have some room we're going to draw here, okay? I'm going to tell you what to draw, I'm going to try to explain this in words, and I want you to tell me what you're drawing, okay? If somebody can figure it out, raise your hand and go to it. I know that seems a little backwards, but I'm going to read it out loud to you, and let's see if you can figure out what this first postulate is all about. Okay, are we ready? Alright, so let me freeze this so it doesn't go away. Hopefully the projector keeps working today. Okay. Alright, so here's what I'd like you to do. I'd like you to draw a line segment on your paper. So draw a line segment, put an A and B at the endpoints. Line segment on your paper. Okay, put A as 0. So put a 0 right above A or below A. I don't know how you want to do this. And pick any positive number for B. Any positive number that maybe your lucky number. Pick any number you want. Now what I'd like you to do is put some more points on the line segment you have, but try to equally space them from B. So put some more points in there. Equally space them from A to B. Try to make it balanced.
Does it have to be multiple? Or
you can do 1, you can do 2, it doesn't really matter. It's up to you how many you want to put. And figure out what those numbers are, now that you've equally spaced them. Now figure out what the numbers go with those dots, because you already picked your number for B. You have to now figure out the spacing for the extra dots you just threw in there. So if you threw 6 dots in there, you better figure out what those 6 numbers are. That's what I want you to figure out. There's a rhyme and reason to my madness that I'm going to talk about. So you got your dots. I'm going to walk around the room and I'm going to check. So they could be decimals. Don't be afraid. They could be decimals. They could be whole numbers. Oh my goodness. It worked. I might use that one as an example.
Please do.
Yeah, you're doing the right thing. And I might actually use that as an example. Okay, that's easy enough. You had a good one. You should see some of those. Oh yeah. Right, yeah, see, there goes one of the hard ones. All right. I think I gave you enough time. You guys got the drill. What are you drawing?
A line segment.
Well, it's a line segment, but what is the thing starting to look like now? Oh, I say it. You're drawing a number line. You're drawing a number line. That's actually what you're doing. What I just explained to you is the wording for the first postulate, postulate 2.8. It's actually how you draw a number line. So I want to go through some of those examples because I thought they were actually really good, really creative. Some of you actually went way beyond what you needed to, but let me unfreeze this so you can, this is postulate 2.8. I'll let you write this down, then I want to go through the example that you guys just did because I want to use it. There's some good ones here. I want to talk about it because we can learn from that. Okay, I'm actually really impressed. We figured out what we're actually supposed to be drawing without any hints. I didn't tell you that. We're drawing, you're putting numbers down. Okay, so ruler postulate 2.8. It actually has a name for this postulate. That's how important it is. It's called the ruler postulate. Any points on a number line, or any points on a line or line segment can be put in a one-to-one correspondence with real numbers. That one-to-one correspondence is huge. That's the part that we were talking about, and that's what I'm going to use my examples, because some of you have really good examples. Any given 2 points, A and B lie on the line. A corresponds to 0, B can correspond to any positive number you want. Some of you picked very tough numbers, some of you didn't. It really came down to how many points you had on there. Try to equally space the dots. It's always funny watching people try to draw this for the first time, because they don't know what to expect. They put their dots there. All right, I'm gonna put 3 dots across, and they're like, oh my gosh, I have to figure out what the numbers are for those dots. Yeah, that's the tough part. Okay, once everyone gets this written down, I want to talk about a couple things. I want to talk about the one-to-one correspondence idea. I want to talk about what real numbers are. I think this is important. We got to talk about this. What is this? Mouse fit? Is that mouse? On my slide? No, it's just computer mouse. Threw me off. Wow. Did I take a screenshot of that mouse sitting right there? Okay, are we good? Everyone's got it? All right, perfect. Okay, here's the idea. I want an example. In fact, Chris, you had a good example. Can I have your numbers that you had on yours? What was your A number again?
0.
A was 0, so he did follow that one right. That is 0. What was your B number?
5.
5. Okay, here's B. You take 5. How many dots did he have in between?
3.
Like that, right? Okay, 3 dots. Okay. This is just one of the examples I saw. This going like evened out. This number had to be 2.5. Like it was just one of those things that he had to be a decimal. It had to be the halfway point because he only had 3 dots between there. Okay, you can't go like 1, 2, 3, 5. Like he was equally spacing. So he had to go decimals. Now he had to figure out what was in between 2.5 and 0. That's 1 1/4. Right? That's the number directly in between. Okay, and then up here, this would be 3.75. It was just one of those things that you had to see it. It was a great example of it. Okay? Now, did we get the right numbers at least? No. But it was one of those things I was like walking around, I was looking at it. I wanted to make sure we had the right numbers. Now, next one. Bree, what do you have? What was yours?
16.
Okay, your B was a 16.
Yeah.
Okay, how many dots do you have in between?
6.
6 dots. That's another good one. Okay, they had 6 dots. There's no middle dot, by the way. Like the middle dot would have been here. This would have been like 8, like right here. That's between 0 and 16. So there's no middle dot. So we knew that like these numbers, this number had to be bigger than 8, this number had to be smaller than 8. What she was doing, and I thought this was really clever, she took 16, because that was the length of her segment, and was dividing it by 6. That's clever. 6 can go into 16. What is that? That can't be 3, it's got to be twice. That's like a 12. You subtract, you get a 4. You have a decimal here, you bring down the next number. 6 can go into 46 times, that's 36. You get a 4, bring down the next number. it'd be 2.6 repeating. Like it wasn't gonna be a nice number. It made me laugh when I saw our number. So this would be 2.66, and then you keep adding 2.66 and add 2.66, and that's how you find, that's just how you find each number. You just keep adding 2.66 until, well, you get back to 16. It actually does work. Okay, it was just one of those things, we had to see it. George, what was your numbers?
0,
Okay.
5 million.
Alright, so it's 0, the lucky number down here, down the road was 5 million. How many dots do you have in between?
3.
Okay. 1, 2, 3. So this was the 2.5 million mark,
Yep.
and this was 1 and
250,000.
250,000, and this is 3 and 750,000.
Yep.
Okay. Like, really tough numbers, right? It's clever. The reason I picked these strategies, number one, making sure we get the right numbers, duh. But number two, if they don't work out nice and pretty, can we find them? That's clever. If they're crazy big numbers, because the whole point of me doing this was, they said this thing had to be a one-to-one correspondence. Every single number had to be accounted for. Every number, didn't matter if it was 5 million, down to 0 or beyond that. You had to have every number. That's what a one-to-one correspondence is. Every number has a dot. There is a place for it. On your number lines, pi is somewhere on there, believe it or not. Pi is 3.14, blah, 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 blah. That's in here. Like in this problem, it might be around here. Pi is right in that general area. Okay, on this one, pi is, I think, generally in this area. Okay, there is a number. There is a spot for every single number, no matter what type of number it is. That's what we call the real numbers. The real numbers is this massive collection of every type of number that you can think of. So it could be decimals, fractions, non-repeating, repeating numbers, that type of thing. The different categories of numbers, if you don't know. First one's natural numbers. That starts with 1 and goes up. There's the whole numbers, which basically just adds 0 to that list. There's the integers, which adds now negatives. And yes, your graphs actually do have negatives. I just didn't allow you to look at them. So, because I didn't want that much confusion going. So there was no numbers going this way, -1, 0, 1, 2, 3. You guys get the idea. You can keep going forwards and backwards. Then you'd have the rational numbers, which are anything you can write as a fraction. So like when Bree was taking her 16 divided by 6, that's a rational number. Because you're getting decimals, you're getting other things. Some people also have to do decimals. But it's anything you can write as a fraction. It's any repeating or terminating decimal can be written as a fraction. And then the irrational numbers are also accounted for, like pi. It's numbers that never end, never repeat. Pi is a perfect one, square root of 2 is a good one, there's just a ton of them. In fact, here's the weird thing about the completeness property. Okay, with all those numbers, that's what allowed you to draw your line in the first place. Okay? It allowed you to draw it because of the completeness. If you didn't have all these categories of numbers, your number line, the line you were drawing, would have been like Morse code. There would have been a lot of breaks in it. In fact, here's the weird part. If you were to combine all these categories of numbers, like add them all up, like you add all the hash marks and you even add all the fractions, they don't even equal the irrational numbers. There's more irrational numbers in this world than rational. So if you think about all the fractions, negatives and positives, there's more of these than the others. These irrational numbers fill in all the gaps. They fill in all the spaces that are between nice numbers. But I want you to see that. A lot of people never get to experience that. They never see like the importance of it. It was important that we actually figure out those numbers. And what makes it hard is that we didn't use calculators to try it, right? You had to try to figure out those numbers. But I thought it was important enough. We had to look at it, okay? All right, let's go to another postulate here. Let's go to another postulate. This one I'm not going to have you draw or anything like that. We'll do another one we'll draw here in a minute. Okay, segment 2.9. I'll have the lights so you can see a little bit better. Segment addition. Postulate 2.9. A and B and C are collinear. What does collinear mean again? Same line. Okay, they're all on the same line. Point B is somewhere in between them. Doesn't matter where, just somewhere in between. That then, so if or B is in between A and C, if and only if you can add the segments together to make the big stick. We've actually done this in the first chapter. So this one is a slight review, just slight. This one is. So A, B, and C are collinear, then you can add segments together. And notice they had to be collinear. They have to be in a straight line. If they're not in a straight line, it doesn't work anymore. So if there's a bend in the road, you can't do this math anymore. Or you can add up two sticks to make a bigger stick. We've discussed this. It was on our first chapter test, not even the last chapter, the first chapter. I think we had two of them. We had problem 4 and 5. Well, it comes full circle. We don't get rid of it, we have to use it now. Because this is going to be a part of our proofs. Can you add sticks up and make a bigger stick? Can you actually see the math that's involved there? We'll do a proof of it today. We're going to actually do one. I'm going to pick out one that we can actually use. The goal is to at least do one of them. So we'll see that. Now, if you want a taste for what we did previously, what we had previously is something like this, right? X plus 2, and 3x plus 8, and we had to get to 36. Something like that. That is something we had to get to. Now, again, this will be a decimal. It's not going to be a nice, pretty number, but you get the idea. Like, that's the types of problems we were doing. Okay? That's what we're going to. So if you're to add the two small pieces together, these are the small pieces, because that's BC and AB. You can add them, and that makes the 36. So you can set up your algebra problem. And this is what we're kind of going to. We're going to be going to a point where you can do this stuff now, and now you can show me every step and every property that would take you down and to get your answer, whatever that number turns out to be. Okay, whatever 26 divided by 10 or divided by 4 is, which is 6 point something. Questions at all? All right. I thought that was kind of important. We got to come full circle. You got to see how to use the stuff we've done previously with groups. Okay, let's get to an example here. I got a couple different ones picked out. This is the one I want to start with. Ooh, yeah. Okay, I'm going to make this bigger. Let's zoom in here. Yep. Okay, well, let's write this down. This is our first example of the day. After this one, we might go to our next postulate where we do some more drawing here. B is the midpoint of A to C. D is the midpoint of C to E. Prove that AB, and I guess you're also given that AB and D are congruent. Prove that AE is exactly 4 ABs. We're doing a lot of adding. Once you have this written down, we'll do the proof of it. Proof is kind of lengthy because there's lots of stuff we have to talk about. They actually give us a lot of givens, but we have to define those things. That's what makes this one a little more challenging. But we're going to follow the same pattern. I have that outline for the proof on the board, where you start with the given information. Line 2, you always redefine the definitions. We have a couple definitions here. We have midpoint stuff, and we also have that congruency symbol. And then we're going to have to do some algebra to get down to a point where AE is exactly 4 ABs. We'll do it today too. Pasha right now, or the example, sorry, not Pasha, but the example. All right, I'm gonna turn on the lights, let's go through a proof. Okay, how do you start a proof?
Given.
Givens, we have a lot of givens here. So, and we're gonna have to define, whoa, what happened? Oh. Oh, that's a shame. Alright, we'll get this going.
Did you have them?
Alright, let me just get rid of that. We don't need that right now. We can go by heart. We'll bring it back here in a second. Alright, so line 1 said that B is the midpoint of A to C, correct?
Yeah.
Okay. Second part, it said that, was it D is the midpoint? Is that correct?
Mm-hmm.
D is the midpoint of C to E, correct? And then the next part, it said that AB is congruent to, is that DE? Is that correct? Is that what they said? Okay, all right. There's our givens, and I'll put the drawing back up here in a second. Computer turned off. Wait, it's back. It's back. Ah. There we go, perfect. Okay. I don't know why I just turned off, but okay. All right, so we have all of our parts. Line 2 of a proof, we need to discuss what these things mean. That's the hardest part. It's like, when you're looking at that outline of that proof over there, we have to redefine vocab terms in line 2. We might have to do that twice before I can even set up a formula so I can actually solve this thing out. This is the challenging part. It's not even getting to the formula. Like the formula, we know at some point, we're gonna have to add things together to get to this mess right here, where it can prove that, AE is exactly 4 ABs put together, 4 of them, right? All right, so line 2, let's define what midpoints mean. What does it mean that B is the middle of A to C on this picture? What does it mean that this is the middle? What can you tell me on, again, this is the stick I'm talking about. What does it mean that that's the middle? Anyone happen to know the definition of midpoint? George, what do you got?
I don't know the exact definition, but it just means that it's the exact middle of the 2 points.
Okay, I agree. That's one part of it. That is one part of it. That is the exact center or middle of A to C. Okay. What else do we know? That is correct, though. You are right. That's one piece. The second piece. What can you tell me about the 2 sticks?
If you add up A and B, it would be the same amount of B and C.
Okay, they're the same stick, right? Yeah. So here's the idea. You're actually hinting at AB is exactly congruent to BC. That is what midpoint means. This is the definition of midpoint. Some people just tend to forget that. They know it's the middle, but the main definition is that the 2 sticks are exactly the same stick. So in fact, I'm gonna put a little hash mark here. That and that should be congruent to each other. That's what those little hash marks mean. AB and BC. Make sense? Okay? All right, and let's keep going. D is the middle of C to E. So what can you tell me if D is the middle? If this is the midpoint of C to E, what can you tell me about those 2 sticks?
They're equal.
They're equal. So CD is congruent to DE. It's important that we know that. We gotta get that. You gotta understand that definition that those sticks are equal. In fact, I'm gonna put little hash marks there. We'll fix those hash marks here in a minute. We'll just kind of see what that means. There's lots of little pieces to this proof. We haven't even got to the algebra yet. Okay, do we understand how we use that definition now? It's important we have to redefine what words mean. Because if we didn't know, like some people don't know what midpoint means that the sticks are equal. Line 3. Usually this line is meant for coming up with a formula. We can't get there yet. We still have words we need to define and objects we need to get to. Like for instance, what do all these symbols mean?
Equal.
Yeah, congruent, equal. We need to write that. Like we need to state that the measure of A to B, if I left a little bar that means to measure it with a ruler, that's equal to DE. Those are equal. That's from the first line. Also from the second line, AB is equal to BC. And CD, that's equal to DE. Like, we have to state those. Those are the things that are obvious from the lines right up above it. We need to get rid of all these congruency symbols and make them all equal. So, this is the definition of congruent. Now again, we're going a little off script because we need to get to a point where we understand what that's saying to us. Now, what this also means, on line number 4, get to my green marker at, I had somewhere. Okay, what this also means is that all of these pieces are equal to each other. Not just that they're equal to the ones across from it, but they're all equal to each other because AB is equal to DE, DE is equal to CD, and AB is equal to BC. So what I can now state, this is a transitive property. Since AB is equal to DE and DE is equal to CD, AB is equal to CD. I can state that because this one's connected here, DE is connected to CD, these two are connected to each other. That is the transitive property. It kind of looks like substitution. It's the transitive property. They are equal to each other. Question?
Would you also need to state that AB is equal to BC?
We already have that. It's in the middle. It's right here.
Oh yeah.
Okay. Why I'm doing this. This is tying up all my loose ends. So why I'm writing like AB is equal to DE and all this, why am I doing that? Because now, this stick is equal to BC, which was equal to DE, which is equal to CD. They're all the same hash mark. They're all the same now. It's not just one piece, there's actually 4 of them. So if we do a little segment addition, we can now substitute these things in and get our final answer. Now segment addition, if you go back and look at what that postulate said, postulate 2.9, how many sticks do you add together to make a bigger stick? 2, right? We're going to have to do some serious work to get down to AE is exactly 4 ABs. The whole thing. You can actually see my hash marks are telling me that. There is actually 4 sticks going across. I have them all marked. They're all the same marking. But I have to get to that because segment addition is actually adding sticks together. So here's the idea. I'm gonna shorten this up so it makes a little more sense because I don't want to go overkill. AE. That segment. What are the parts that add together to make AE? Like what are, instead of just adding 2, what are all the pieces I can add? AB, okay. What's the next one?
AC,
No, just give me the pieces, these.
BC,
BC,
and CD,
CD, which is, and then the last one.
DE.
Okay, boom. Does that make sense? What I'm writing there is segment addition. You're adding small pieces to make a big piece. So again, this is line 5, that is segment addition. Now typically segment addition is used for just adding 2 parts, but you can shorten it up to make 4. I can add each one of these little pieces together, and that makes the full stick. That's common sense. They're all collinear with each other. It is a segment all the way across. Okay. Now, I'm going to start substituting things in. I'm going to take out these pieces and let's plug in what they're equal to. What are these things all equal to? What's the one thing they're all the same?
Maybe.
They're all ABs, if you notice that. Like DE on the very end there, that last blue arrow, that's also an AB. BC, the one in the front, that one can be an AB. The CD, which we just said in line number 4, those can be replaced. So on my next line, line number 6, I can now substitute in ABs for everything. Because these are all the same as ABs, so I can plug these in. This is just simple substitution. Because we already said that AB is all the same as those other ones. So that reason would be substitution. Line 6, substitution. Now, what do you get when you add them all up? How many of ABs are there?
4.
4. So, this is your last line, line 7. So this one actually won't one extra step. Dot, dot, dot. Now what you have is you have AE is equal to 4 ABs. Because when you add them up, there's 1 plus 1 plus 1 plus 1. There's all one of these, so that adds up to being 4 of them. And that's doing simple substitution. That's simple arithmetic. Substitution. Now, there's different ways to do this proof. I've seen it different ways. I think this is probably the most elegant way of doing it. But without knowing that all these things were equal, you wouldn't have been able to substitute them. And obviously, line number 5, you have to know that you can add sticks to make a bigger stick. You can add all 4 sticks to make a larger stick. That's segment addition. Okay, questions? All right. All right, what we'll do, let's save the rest of the 2 other postulates I was going to do today. Let's save those for Monday, because obviously we only have 5-6 minutes left here. I want to give you some time where you can actually work on your page 139. That's due on Monday. Keep that in mind. That's the one where you, like the first 4 problems, 1 through 4, is just one property. What do they do from the left to the right? There was one property they did. 5, they already have the whole proof given to you. You have to fill in the blanks. 6, 7, same thing. 8, 9 through 15, I think there's 1 or 2 where you have to just give me the one property they're doing. 17, 18, the whole proof is provided for you. You just have to give me the blanks for 17, 18, and then 23 through 26, you have to do the actual proof. So take your time. Not bad. Well. Okay, stop here. Question?
Yeah, I just want to make this now.